Hey, welcome back. We are still talking about electricity, static electricity, and moving on into Coulomb's law. So Coulomb lived about the same time as Newton. So you can imagine that there was a whole lot of ideas floating around at that time dealing with forces, dealing with objects not touching each other, and just a whole bunch of science that's happening with that. Now, as Newton dealt with gravity and masses, Charles Coulomb was looking more at forces and charges. So we named the unit of the Coulomb after him. 1 Coulomb is how much 1 amp will produce in 1 second of charge, how much charge it pushes in 1 second. Another way to think of it is if you have a 100-watt light bulb, that's about how much charge is passing through it every second is 1 Coulomb's worth. Now, it is a really, really large unit. Notice that it is not the charge of 1 electron. So 1 electron is 1.6 times 10 to the negative 19th Coulomb. It's a very, very small the electron is a really, really small charge. The Coulomb unit itself is really big. So it takes 6.24 times 10 to the 18th electrons to make 1 Coulomb. That's the difference in that. Moving on then, when we talk about the law, he says that the force is directly proportional to the magnitude of the charges. So we have this, the force is proportional to the little charge and the big charge. He also said that it's an inverse square law, that because they are not touching each other, it's a force over a distance. There's a field involved with that. And that as you get farther and farther and farther apart, that force drops exponentially. And so that's why we have that 1 over r squared value for that. If we take and put those two together, we get that the force is proportional to the two charges divided by the radius squared. That should look really, really familiar to you. If I want to get rid of this proportionality sign and I want to turn this into an equality, what do I have to do? That's right. We have to add a constant. So we add this constant, which is the K value here. And this is what Newton's law, or Coulomb's law is, that the force between two charges is that KQQ over r squared value. Now, if you think back, that should look really, really familiar to one of the other equations that we studied in the fall, and I have that up on the screen, which is the GMM over r squared. So this was Newton's gravitational law at the bottom here, and at the top is Coulomb's law for static electricity. So there are a bunch of similarities and a few differences that we want to highlight for this. So they should look familiar to you. Notice or remember that gravity, for now, all we know, is that it's only attractive, that the two masses will only ever attract each other. They will never repel each other. As opposed to when we talk about static electricity, we have the two different kinds of charges, the plus charge and the minus charge. So there are two things that can happen. Either the opposite charges will attract to each other, or like charges will repel away from each other. So that's comparing the forces. When we talk about the fundamental values, so the Newton's law is dealing with the product of two masses. When we talk about Coulomb's law, it's dealing with the product of two charges. We can look at them and say they are both inverse square laws, that force drops off exponentially the farther away the two objects get from each other. And then the last thing to do is to compare these two constants. So remember that the gravity constant, that G value, is super, super, super small. It's 6.67 times 10 to the negative 11. That's why you need so much mass in order to have any force. That's why for you to be attracted to the Earth, you don't have a lot of mass, but the Earth has a whole honking lot of mass, and that's why you get pulled towards the Earth. Technically speaking, small objects around you are attracted to you, but again, your mass is so small, their mass is so small, it doesn't overcome that number. Now, interestingly enough, whenever we talk about the K value for Coulomb's law, that number is a really, really big number. So it's 9 times 10 to the positive 9th. So you'll notice that if the gravity one, it takes really big masses to overcome that constant. When we're talking about electricity, it does not take really big charges to overcome that constant, because that constant already is really big. So those are some of the different things that you can compare. So 3 sample problems here that we'll run through, just sort of a quick example. What is the magnitude of the electrostatic force between 2 protons in the nucleus, and assuming that the distance is 3 times 10 to the negative 13th. So if you remember, we're looking at Coulomb's law, F equals K Q Q over R squared. That we're looking for the force. The K value is a constant that is always 9 times 10 to the 9th. And the charge of the proton, remember, is 1.6 times 10 to the negative 19th. And then the charge of the other proton will be 1.6 times 10 to the negative 19th. And it tells us the distance that they are away from each other, 3 times 10 to the negative 13th. And it looks like this is in centimeters, so I'm going to have to put that into meters. Remember that centa is 10 to the negative 2, which means I'm going to go 3 times 10 to the negative 15. And then the most common mistake is students forget to square that value whenever you do that and plug it in. So when we do that, if you punch all that number in, you should get a force of 25.6 newtons. 25.6 newtons. And notice that's a really, really big force for two so small objects that you can't even see them. We can only look at them through electron microscopes. So 25.6 newtons ends up being the force for that. Now, to kind of throw into the next part of this, we could say, here we go. What is the magnitude of the gravitational force between the two protons? So if I'm talking gravitational force now, aren't I going back to that GMM over R squared that we had earlier? So 6.67 times 10 to the negative 11 is the gravity constant. And then our mass is going to be 1.67 times 10 to the negative 27th times 1.67 times 10 to the negative 27th. And that's all going to be over, again, the distance of 3 times 10 to the negative 15th. So remember, I'm converting that centimeters into meters. And then don't forget, you have to square that. And when you punch those numbers in, assuming I got all of those right, and remember those, which I should have, but you never know. Then when you punch those numbers in, you should get 2.07 times 10 to the negative 35th newtons. So notice how way, way, way smaller that force of gravity is compared to the force of electricity. So the force of electricity, if you remember, was the 25 point something or other newtons. So 25 newtons versus 2.07 times 10 to the negative 35. So gravity is way, 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 way smaller than the electric forces. Okay, moving on to number 3. If these protons were released from if these protons were released from rest, then what would their acceleration be? So remember, for acceleration, we can just do F equals ma, and we can take and plug in and say that 25 point, I think it was 6, I'm just going off memory here, minus the 2.07 times 10 to the negative 30, was it 31? There we go, 35. And let's go back here a second. 25.6, I was right. So 25.6, negative 35, 2.07, negative 35. And then the mass of the proton is going to be the 1.67 times 10 to the negative 27 times A. And if we punch all those numbers in, then we should get a 1.53 times 10 to the 28 meters per second squared. So notice that because this force of the electricity is so big, that acceleration of the proton is going to be really, really big too. Now, we're not really going to do much of that where you're finding the acceleration like that. We're rarely going to do this where you're plugging this gravity in because we've already done that. What we really want to do more is focus on Coulomb's law, that's this KQQ over R squared. So when we talk about giving you two charges, finding what the force is between those two charges. And you can think through, if I change my ink color here, maybe to orange. So I have a charge here, I have a charge here. If this is a plus charge, this is a plus charge, then these two charges have an equal and opposite force that will pull them together of 25.6 and 25.6. Later we'll say, well, what happens if I have a negative charge here and a positive charge? I'm sorry, I drew that wrong. So these are two plus charges. Opposites attract, like repel. So these are going to push away with 25.6, and they're going to push themselves that way. And that's one of the ways that the physicists looked at it and said, hey, if I have my two protons in the nucleus and a neutron and an electron out here, and an electron out here, then what is keeping those protons in the nucleus, because they want to push away according to Newton's or Coulomb's law. So there has to be another force in the universe that's stronger than the electric force that is actually pushing them back towards the center of the nucleus. And that's when we get into the strong nuclear force. So that's just a bonus. You don't have to know that. It's just something that's really cool. You can look that up on your own later on. Okay, so moving on, that's that. When we deal with a plus and a minus charge, now notice that these two will attract, and so I'm going to have a 25.6 and a 25.6 if it's one proton, one electron. And notice that our direction is really going to be dependent upon which one of these I'm talking about. If I'm talking about which way is the electron being pulled, then it will have a positive 25.6, and which way is the proton being pulled, it will have a negative 25.6, because remember Newton's third law. Every force has an equal and opposite force, and those are our two equal and opposite forces that deal with that. Then lastly, what we'll do in the next one is we'll talk about, well, what happens if I have a charge that is a negative here, a positive here, and maybe another negative here? What's the net force acting on this charge? So these two negatives will repel. These two positives will attract. I can do my KQQ over R squared for these two. Then I can do again the KQQ over R squared for these two. And because they're going in certain directions, we can add those up like vectors because forces are a vector. That's sort of a small hint of where we're going. But for now, we're doing basic just KQ over R squared, plug and chug in those values, and do that. If you have any questions, feel free to contact me.